Hello. Today we are going to look at um, a type of ordinary differential equation which we have analysed in the past because I have a slightly new technique for solving it, and the equation in question is if I can find my pointer, there we are. So the equation in question is x double dot plus 2kx times x dot. At least I think we've solved this type of equation before in the past. So we've got x double dot plus 2kx x dot plus a times x equal to 0, and we'll call that equation 1. Right, so this is a lot more tricky to solve because of this factor of x in front of the x dot. And in fact, it's actually non-linear because of this fact. If that x had been a t, or there'd been a t there, or a t there, then this would still have been a linear ordinary differential equation. But in this case, it's a non-linear second order ordinary differential equation. So how do we go about solving this equation? Well, what we say is, if I can just turn to red ink, we let x dot, which we know is dx by dt. So we let x dot equal dx by dt, and we'll give that another name. We'll call it v, or nu, or whatever you want to call it. So x dot is equal to nu. This means that x double dot, which we know is d squared x by dt squared, is equal to dv by dt. But the problem is, if we substitute that into there and v in here, we end up with a v, a t, and an x, and we can't have that. We can only have at most two variables in an ordinary differential equation. You can't have 3 or 4. So what we do is we use the chain rule over here, and what? Oh, excuse me, it's doing something weird. There we are. So let me just, if I just delete that, then we can put the dt over here, and we'll write dx there and dx there. Okay, so now you can see if we cancel those dx's, we're still left with dv by dt. But of course, writing it like this means that we can substitute v in for dx by dt, right? So this becomes v, or nu, d nu by dx. I suppose I should really refer to this as v. So v dv by dx. So if we substitute this in to x double dot and this v in to the x dot, we then have an ordinary differential equation in terms of only v and x, not v, x and t. So let's go ahead and start to solve this equation. So what we have, if we substitute this and this into equation 1, we have v dv by dx plus 2kx times v plus ax equal to 0, and we'll call this equation 2. Now, this is a special kind of equation called a Chini equation, but sometimes it's called an Abel equation, right? So it's either a Chini or an Abel equation. And we rewrite this equation 2, rewrite equation 2 as v dv by dx plus ax equal to minus 2kx v, right? And we'll call that equation 3, right? Okay. So, according to George Moseley Murphy, and I'll write his name down here, George Moseley Murphy, in his 1960 book, now reprinted, so it's now reprinted, and it's something like nonlinear ordinary differential equations. You would have to look that up. He states that, and we'll go on to, let me see if I can scroll down. No, I can't scroll down very far, can I? So let's go on to a new page. He states that a solution to equation 3 here is the following. So if I just minimize that and go on to the next page. So Murphy states that a solution, you could say an admissible solution to v dv by dx, and I'll have to go back and just have a look at that equation. So we've got v dv by dx plus ax equal to minus 2kx. Oh, I think I made a mistake there, unless it's gone off the page. Let me just make that. All right, no, I didn't make a mistake. So v dv by dx plus ax equals minus 2kxv. So we need to write that down. Okay. So a solution to v dv by dx plus ax equal to minus 2kxv, we're still calling that equation 3, is v equal to ax. So it's this divided by this. Okay, so that becomes ax over minus 2kx. If, and I'm not sure about this, but I think it's if and only if dv by dx is equal to 0. So let's see if this condition that dv by dx is equal to 0. Okay, so we've got this solution here. You can see that the x cancels, leaving us with v equals minus a over 2k. And if we differentiate this, then we find that dv by dx is equal to 0. So why does this help us? Why does knowing that dv by dx equal to 0. Why do we know that that helps? Well, we've got equation 3 here. So if we rewrite equation 3, just let me go on to another page. So if we write equation 3 again as v dv by dx plus ax equal to minus 2kx v, then since v is equal to minus a over 2k, because the x's have cancelled, and dv by dx is equal to 0, then the left-hand side of equation 3, so we'll just call this equation 3 again, the left-hand side, which is this, is equal to, well, we've got v, so we've got minus a over 2k times dv by dx, which is 0, plus ax, which is just equal to ax. Now the right hand side of 3 is equal to minus 2k x, let me see, 2kx times v, which we know is minus a over 2k, which is equal to, well, as you can see there, the 2's cancel, the minus cancels with the minus, and the k cancels, leaving us with ax. So the left hand side equals the right hand side. This is exactly what we want. We know the equation is satisfied with the solution of v equals minus a over 2k and its derivative of dv by dx equal to 0. So what does this tell us about the original second order ordinary differential equation in equation 1 here? Well, if we just write this down again, so we'll go to a new page. So we've got let me just change to black ink. So since the original ODE was or is x double dot plus 2kx dx by d, sorry, we're not writing it like that, are we? So 2kx x dot plus ax equals 0, and this is our equation 1, right? And I'm just double checking that. Yeah, so since we've got that, and v is equal to, what did I say, minus a over 2k, right? Have I, yeah, I think I've done that right. Just let me double check. Let's just go back to this. So v equals minus a over 2k. So we know, but since we know that v equals x dot, and we'll rewrite that now as dx by dt, then x dot is equal to minus a over 2k. So in other words, dx by dt is equal to minus a over 2k. This can be integrated to give the integral of dx equal to minus a over 2k times the integral of dt, yielding the solution. Let me just write that more coherently, meaning that a solution is x equal to minus a over 2kt. Now just leave it like that. Don't bother adding a constant on. That will be complicating it in this case. So I'm saying that x equals minus at over 2k is a solution. How do we know that this is a solution of this equation? Well, we differentiate x, okay? So let's do that. So let me just go to another page and let's maximize that. So we'll just rewrite equation 1 at the top. X double dot plus 2kx x dot plus ax, let's make that look more like an x and that more like an x, equals 0. So that's equation 1, and we have that x equals minus, and I have to look at what we did before because I can't remember. Where's it gone? There we are. So x equals minus at over 2k. Right. Minus at over 2k. So I'm saying that the solution to equation 1 is this expression here. Well, if we differentiate this expression, if we differentiate x equals minus at over 2k, then we get x dot equals minus a over 2k, because the t just disappears. The x by dt leaves you with minus a over 2k, and if you differentiate this, you get x double dot equal to 0. So the left hand side of 1, which is x double dot plus 2kx x dot plus ax is equal to, and I'll write it under here because there's more space. So we know that x double dot here is, why has that disappeared? Let's just make that clearer. Make it look more like a dot. So x double dot is 0 because we've found that from here, plus 2kx. Well, x is minus at over 2k, times x dot, which is minus a over 2k, plus ax. So what's that come out to be? Well, we can do a bit of cancelling. So the 2k here cancels with the 2k there, and oh yeah, what have I forgotten to do over here? Well, let's just let me see. Let me just where's the eraser? I can't find an eraser here. So we'll just go back and put in the value of x there, which is minus a over 2k. Right, now that's equal to, like I said before, the 2k's cancel, leaving us with, oh, and also the minus sign cancels with the minus sign there, leaving us with a squared t over 2k plus, well, it's going to be a minus, isn't it, there, because it's a times a minus a, which is a squared. Oh, and there should be a t in there as well. A squared t over 2k, and that's equal to 0. So therefore, substituting x dot equal to minus a over 2k and its derivative x double dot equal to 0 back into the left-hand side of equation 1 yields 0 as necessary and required. So therefore, this is, we'll write it, this is the required solution, as when we substitute everything into the left-hand side is equal to 0. Okay, so that just about concludes that for this video. Suffice to say, just one more thing, that there is a second solution to this equation, and I'll just very quickly explain how that is found. So I'll just write down, there is a second, I suppose you could say linearly independent, although with it being a non-linear ordinary differential equation, I'm not sure you could call each solution linearly independent. I would assume they are in this case, but they're not always bound to be, as I understand. So we'll say there is a second, in brackets, linearly independent question mark solution, and that is found by writing x equal to x1 times the integral of e to the power of minus the integral of p dt, all divided by x1 squared, and that's integrated with respect to dt. And I'll just very quickly go through what p actually represents and what x1 represents. Well, we know that x1 is equal to our our first linearly independent solution, x equals minus at over 2k. So that's minus at over 2k, right? x1 is equal to that, and p is equal to, well, let's just go back to the original equation here, and we would find, let me just maximize the screen and change to green. So p is equal to this term here, p, right? So 2kx is p. If I just go back to that page, so that's equal to 2kx. I'll keep it in green. Of course, it's actually 2kx1. So where am I? Let's just go back to black. So that's equal to 2k times minus at over 2k. So p is equal to minus at. So what you do is you substitute that and that into that equation, and you will get your second linearly independent solution. But I'll leave you to do that as an exercise. So that brings us to the end of this session on nonlinear ordinary differential equations, specifically the solution of the equation x double dot plus 2kx x dot plus ax equals 0, and hope that that has been helpful to you. So I'll leave it there for now and bid you farewell. Okay, until next time, goodbye.